Hello and welcome to another video. In this problem we're going to be focusing on unique paths. So we have an m by n grid in this problem where m is the number of rows and n is the number of columns, and we have a robot that starts at the top left and we're trying to get to the bottom right. And we need to figure out how many different ways can we get there. So for this first example it is 28, and for the second example, if we take a look, this one's a little bit easier to see. So we have 3 rows and 2 columns here. So we can just say, okay, let's just have this. And let's have 3 rows. So we start at the top left, we try to get to the bottom right, and let's actually look for all the ways, right? So one way is you go like this. Another way is you go like this. And then last way is you go like this. And those are the 3 different ways, and those are the only ways you can do this. So essentially at every row, you have the option of going down or right, unless you're all the way at the end of one of them, right? So for example, let's actually go back, and let's actually maybe redraw this big thing to make it easier. So there we go. And we don't need to draw like every single row. We'll just draw a couple and a couple columns and things like that, right? Just to kind of do that. So let's just say we have like a couple rows. So essentially at every row, we have the option of going down or right. Now, obviously, if we are all the way to the right, then we can only go down. And if we're all the way down, then we can only go right. And so if you have this problem where you can go in multiple directions, the number of paths from some point, say here, is, because you can go left or right, is the number of paths going this way plus the number of paths going this way, right? And so that's how you do it. At every single point, you can either go left or right or down. And so you would just add those up. You say like, okay, let me go right and figure out how many paths there are there, and let me go down and figure out how many paths there are here. And then essentially, once you get to the end, then you are done. And so how would you do this in like a, let's just go through this in a memoization solution. And the way it would work is once you get here, you're going to say 1, as in there's one completed path here. So you would just say like, okay, I'm going to like what are my base cases and things like that. And also notice one more thing, and this is why you're going to want to do memoization. And this is one of the easier DP problems. I don't want to draw an entire decision tree, but I will quickly show you why you need caching. So the number of ways to get from here to here doesn't matter how you got here, right? Like if you get here this way or you get here this way, it doesn't really matter. Once you're here, and nothing else matters. But how many different ways can you get here? Well, let's take a look. You can get here this way, you can get here this way, and you can see like you're going to be getting here twice, and then you're going to be calculating the number of paths from this point twice. Well, that's super inefficient, and as this gets bigger, you're going to be able to get to the same place in a bunch of different ways, right? So as it gets, like farther and the grid gets bigger, there's going to be a bunch, right? For example, here you can go like this, you can go this, there's a bunch, right? There's more than that, and so on, right? So you're going to be going to the same place multiple times. So that's why we're going to want to have caching and memoization, and we're just going to say like, if we were here before, let's just get the answer we had before. We don't want to do it multiple times. So yeah, I could draw a decision tree to show that, but I think this is a little bit cleaner just to show like if you can get to the same place multiple times, you're going to be doing the same repeated work, you're going to want to memoize. So for memoization, you need 3 things. You need a state. And so for the state, this is pretty straightforward, right? It's just going to be the row and the column we're currently on. Right? That one's pretty straightforward. Okay. What about for the actual base case? Well, for a base case, you could do a couple things, right? So you could say, you could make sure that you're not out of bounds, right? So when you go, like let's say you're over here, you want to make sure like, oh, I don't want to go here. So if you are checking for that in your actual recursion, then you don't need this base case. But if you are not, then you need it. So base case out of bounds, return 0 as an invalid path. And then the other base case is get to the end, return 1 as a valid path. Right? And that's pretty much it. Okay. Well, what about the recursive case? So for the recursive case, we have a few options as well, right? So we can either go right or down. And basically our number of paths equals number of paths going right plus number of paths going down. So it's pretty straightforward. We will just say our solution is just the dp of the row increasing by 1 plus the dp of the column increasing by 1, and then we finally get a solution. So that's pretty straightforward. And that's essentially what it is. Like if you're here, you're just gonna say, okay, like this is dp of 0, 0. Well, the dp of 0, 0 equals the dp of 0, 1 plus the dp of 1, 0. Right? You can either go this way, and you have to figure out, well, like what's from this state and what's from this state, and both of these together are going to be this one here. And so now we have enough to code it up, so let's do that. So let's code up a memoization solution. So we're going to say, we're going to have this visited, right? And we're going to say def dp row. We can actually get rid of this. Column. And we're going to say if row. So we're going to check if we got to the end, row column equals m minus 1, n minus 1. Then we're going to say return 1 because that's the finish line, right? And we are going to check in our DP manually ourselves to make sure we never go out of bounds, right? So we'll say like if we're at the bottom row, we never go out of bounds. But we also need to check for visited, right? So we're going to check for visited here. So we're going to say if row column visited, let's return visited row and column. And now we're going to initialize the result, and we're going to say if we can go, so if we can go down a row, right? So if we can go down a row, let's try it. Let's make result equals 0 as our initial value as well. So if we can go down a row, let's try it. Res plus equals dp of row plus 1 column. And same thing for the column. If we can go down a column and not be out of bounds, then let's try that as well, right? So res plus equals dp of row and then column plus 1. So pretty straightforward. You just have two options. You either go down a row or to the right. And you add those together, and then we memoize. So visited row column result and return result. And then finally, we just need to return dp of 0, 0 because that's our starting point. So let's try that. See if it works. And you can see it does work, but it's not super efficient, right? So what we're going to do here is now we are going to comment this out, and we're going to talk about how we can make this more efficient. And normally for a bottom-up DP, you can't really make it more efficient because the space and time is the same. But we're going to show how we can do that for this problem. We're actually going to go over this one in particular with the 7 by 7. So it's the 7 by 3. So let's do that. So let's go draw this. And we're going to have it, because I think for these easier problems, it is important to really because these problems are pretty straightforward, you're going to want to really try to do the difficult stuff for these. So then you can at least attempt it for the harder ones. So we're going to have 4, 5, 6, 7. Not super even as always, but good enough. And now we are also going to actually label these rows and columns just to make that easier for us as well. So 0, 1, 2, 3, 4. I don't know why this is blue. A little weird, but we're going to leave it as that. Okay, actually, probably delete it and then put in a new one with green to make it a little better. So let's just do this, there we go. Okay. So essentially now, and let's use another color for the, oh, I see, it's because, okay. Oh, there we go. So now let's actually do this, and hopefully this doesn't change the color of it. Okay, nice. So here we know, we're gonna make an array this time. That's gonna look like this. It's gonna be a 2D array, right? We're gonna initialize this state to be 1 because this is like the finish line. And now we're gonna work backwards to get this somehow. Well, we know that at every state, right, the number of paths is the paths to the right and down. So instead of going from here, we're going to go backwards, and we're just going to go row by row, and we're going to fill it up backwards. So here, for example, the number of states is the number of states going down and to the right, but obviously we can't go down, so that's not valid, so we can only go right. So it would just be, we'll just take this value, put it here, and this like this. And that makes sense because whenever you're on this bottom row, you can only go right? Because there's only one path. You can only go this way. You can't go down. So the initial part of this DP is just going to look like this. And now we are going to start filling it out from here. So from here, we're going to go right. There's nothing. And then we're going to go down, and there's 1. Okay. Here, right and down, 1 plus 1, 2. Here, right and down, 3, 4, 5, 6, 7, right? Every single point, right and down. That's how you get it backwards. Now we're going to go here, F7. Now we're going to go here, right? So 1, 3, 6, 10, 15, hopefully I did this right, 21, 28, right? Right and down. So we just fill this out backwards, pretty easy, and you can see it is 28. So that's how. So that you can easily make a function that does this, right? You can just say like, let's just make a DP and let's just go row by row. You know what the state of whatever I'm at is just the state of the row below and the column below. And then if the column below is out of bounds, let's not use that. And if the row below is out of bounds, let's use that, right? Totally doable. But there is one more optimization. There were actually two more optimizations, but I'll talk about the first one first, and then yeah. So notice that for every single row and column, we are just checking the two states below it. So if I'm over here, I'm never going to be checking some row down here, right? I only need the elements right below it and to the right. And so if you think about it, what you could do is, let's say we just filled out this row. Well, what are the elements below this row, right? The elements below that row is this row. So we can just say like every time we fill out a row, that row is the elements below the current row we're trying to fill out now. And then we have those, and then all we have to do is add also the elements to the right, and that would be that row. So just to give you an example here, let's actually make a new thing here, and let's show you kind of how that works. I don't want this. I want this. So now essentially we're going to make a one-dimensional array, and we're still going to use all the same stuff. But now we're going to show you how, instead of making this a one-dimensional array or a two-dimensional array, you can make a one-dimensional array. So basically, this first fill out, and we are also going to draw the row and the, like what the row and the column are symbolized as anyway. So this is only going to be a one-dimensional array, but we are going to show what the row and the column are symbolized at. So this is supposed to symbolize row 2 of this two-dimensional array. And we're going to fill that out first, right? That part is pretty straightforward. We're just going to fill that out with all ones, right? Because when you're at the bottom row, there's only one path to the right. Okay, but now remember that this row is these bottom values for this middle row, right? So we can get this middle row. We already have the bottom values, but now we also need to get the values to the right, right? Remember, for each element, it's the value to the below and the value to the right. But we already just got the values below. So now all we have to do is get the values to the right. So for example, here, there's nothing to the right. Here there is, right? So this is going to be 2, value to the right. And remember, you add what you currently have to the value plus the value to the right, because what you currently have is what's below this row, right? So we have that in place. So now it's going to be like 3. You add this number to this, 4, right? Whatever you have plus the value to the right, 5, 6, 7. So you can see now this row is the same as this row. And now these values are the values that you need for the values below this row, right? So this middle row is the bottom values for this row here. So we're going to kind of do the same thing. We're going to say, okay, well, if those are the bottom values, now to get this whole row, now we just need the right values because we already got the bottom values. They're these. So now we're going to do the same thing. We're just going to take, and so when we fill this row out, this was actually represented as this row here. But now we are going to be representing it as this row here. We're essentially like moving up a row. So we're going to do the same thing. We're going to take these values and then add the values to the right. So we're going to say, okay, so 2 plus 1 is going to be 3, right? Then we have 3 plus 3 is going to be 6. Then we have 10. And you can see like you're literally taking the value you have and just adding the number to the right. Because you already have the value below. The value to the value below is what you started as, right? The value below this was this value. So we already have that. So now we just need the value to the right. So 15, then we have 21. So 21, and then finally 28. So you can see how we did this, right? We basically said, okay, we'll start out with this row. And now for every row that we're trying to build up, the bottom numbers are the row we currently have. So now we only need these numbers to the right, right? So just to show you in this picture one last time, if we're trying to fill out this middle row, in order to get the middle row, for each number, it's the number below it and the number to the right added together. We have the numbers below it already in place, and now we just need the numbers to the right. So that's why I said, like, you take this 1 and you add 1 to get the 2, you take this 1, you add the 2 to get the 3, and so on. And now we saved ourselves some space. And because now this is actually, so right now the solution is if it's m by n, our solution is n space, but there is one other small optimization. Because notice how if you have this, the number of paths for this is the same thing as, I don't know if I can actually do this, but let's try it. So the number of paths, okay, I wanted to copy this entire thing. Let's see if I can. Okay. And now, I don't know if it lets me do it, but okay, it does. Perfect. So let's just actually get more space. So the number of paths for this is actually the same as if it was this way, right? So the number of paths of a 3 by 7 and a 7 by 3 is literally the same, but, and all the operations are literally the same, but because I flipped it, now my space is only 3 as opposed to 7. So the other small optimization you can make is you could say, okay, if m is less than n, right? Because right now I am storing, for this optimal solution, I am storing n elements. But what if m is like 3 and n is 100? Well, then I'd want to swap it. So I'd want to do, unique paths of 100 and then 3. And that way my array would be 3. Yes, I'd have to go up more and fill up more rows, but now my storage is way less. So that's the other optimization you can make, is you can realize for this unique paths, the unique paths for this and this is exactly the same, right? It's still the same thing. You just have more rows for one and more columns for the other. But because we are going row by row, when we flipped it this way, we used way less space. So that's the final optimization. So now we can actually code that part up. So let's actually, we'll keep this, and I'll provide in the code. So what we want to do is we want to say if m is less than n, let's just return unique paths of the other way. So it's actually going to be self.unique paths, and m. Because it's literally the same exact number, but because we're storing row by row, now the rows are smaller. Okay. And so now we need to actually make this DP array. And like I said, for the very bottom one, as you can see in this picture, for this very bottom row, it's all going to be ones because you can't go down. You can only go right. So there's only one path to the right. So we're going to say DP equals 1 times n. So we just built up a row, right? A row has n columns. Now, essentially, we're going to be doing kind of the same thing, except now we're going to be looping backwards. So we're going to say for row in range, and we're going to want to make sure we never go out of bounds. So if you look for the rows, we're going to start filling out rows from this row. So if the number of rows is 3, the row I want to start at is 3 minus 2. And for the columns, I don't really need to fill out these columns because for the columns, remember the down value is going to be calculated for you. But you need to, or sorry, the down value for every column on the right is also 1, right? As you can see, because you can only go down. So we don't need to fill these out. We can just not touch them. So we need to start filling out columns from here. So if number of columns is 7, then it's 7 minus 2, and same thing for rows, 3 minus 2. So we're going to say for row in range, m minus 2, -1, -1, and for a column in range, n minus 2, -1, -1, right? And we are filling out one row at a time. That's why the column is the inner one, because we're filling out the column, like we're filling out the row one row at a time, and we're going through the columns for each row. So then we're just going to say DP column. And like I said, we have the down part already because we optimized. So we're just going to say DP column equals DP column plus 1, right? We only need the right one. And we're sure not to be out of bounds because we did this check, right? Where we're not filling out the last column. So if column was like 7, we'd start at 5, and then 6 wouldn't be out of bounds. And then finally, we want to return DP of 0 because we want to fill this out row number of times, and then this first value will be the value we want to return because that's the total paths. So we would want to return DP of 0. And let's see. There we go. And so now you can see it's a lot more efficient, and space-wise, I think a lot of people have a similar solution. So, but you could see like it's 16 now, and if you had something else, it would be a lot more, right? So I think actually for some reason this also gave me 16, but when I did this earlier with memoization, yeah, let me actually try this again. It should be different, but it also depends on the test cases, like I said. So here we have. It's about the same, but in theory, it should be a lot less. So I'm actually going to comment this one out. But yeah. Okay. So let's actually. Oh, I think the reason why this space one is not great. Yeah. So you can see it's like 16.5 here. It is a little bit less of this. In theory, it should be a lot less. There's also a math solution, which I think is like big O of one space. That's why it's not doing like super well. But a math solution is not something that you're going to be doing during an interview. So this is as good as you can get for this problem. Okay. So let's go through the time and space. So for the time for the memoization solution, you do still have row and column, right? You do still have like this kind of nested for loop. You have row times column states, which is n by n. And then at every single state, you only have two choices, so that's O of 1. But since you have m by n states, it's going to be m by n. And for the space, we are storing a visited set that's also m by n, because you can have r rows and c columns. But for this optimized bottom up, the time is also m by n. As you can see, it's a nested for loop, right? So we're going through rows and columns. But for the space, now we have the O of the minimum of m by n. Because we're essentially saying, hey, if the rows is, let's just take the smallest value of the rows and the columns, and let's use that to hold our variables, as we're doing here, right? If m is smaller than n, let's just make m the columns instead. So that's going to save a space. So instead of quadratic space, we have constant time space, and we're also optimizing for the better one of the variables there. But yeah, I think that's going to be it for this problem. I definitely would encourage you to do this one because this is as easy as it gets for DP. So this is the good one too. Practice bottom up, practice best optimized bottom up, practice as hard of an algorithm as you can get, because for the hard one, that's going to be very difficult. And also for a lot of other ones, you can't actually space optimize, because for this one, you are only checking like the value over here and over here. But for a lot of the hard ones, you're going to have to check values that are like way down or way forward, and then you can't space optimize. So. But yeah, that's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.